So welcome everyone, and welcome to our session this morning. My name is Annie Burgess. I'm the lab director here at ESIP, and you're in the Improving Fairness in AI/ML and Geosciences. Just a reminder, if you aren't overly familiar with Zoom, that there is a reactions button on the bottom where you have a hand raise feature if you do have a question, though we do encourage you to add questions to the chat. We do have a code of conduct that if you are not already familiar with, I'd encourage you to click on at the bottom of the Google Doc here. The session is being recorded and will be available after the meeting. So with that, I guess, Jensen, would you like to kick things off, or I will turn it over to the session leads to take it away.
Sure, Annie. Thank you so much. Good morning, everyone, and welcome to this session about how to improve the fairness of AI and ML in the earth science. And the idea of bringing up this topic is we think that there is some terminology, conflict between the AI community and the earth science community, because we all know that fairness has some specific meanings, but in AI community, fairness means like equity, or the model has to perform the same or neutral role in the daily scenarios. So we would love to hear the community's voice on these two things, and also we would love to see how things going in around the ESIP community, especially the ML related cluster, and see how things has been done in the past year. So I'm gonna pass the speaker. Today's first speaker is gonna be our invited speaker, Daniel Skate from ERUC, I suppose. So Daniel, would you mind?
Yep, sounds good. Let me give me a second to share. Okay. Does this look okay? Everybody can hear me?
Yep.
Yes, good, Dan.
Yes. Okay, very good. Yeah, so I'm going to talk about some work that Fotis and I have been trying to lead over actually about a year now, I guess, and we're kind of getting to an interesting point. So I guess the first thing I should say is that we are both interested in how to think about fair, findable, accessible, interoperable, and reusable in the context of machine learning. And mostly in the case of machine learning models specifically, but not entirely. So let's see, and I'll make the slides available afterwards. I don't have a good link for the minute, but hopefully this will work. So I think it's worth just starting off with fair overall. So the idea of fair started being discussed in 2014 and then was published in 2016 in this paper that's in the on the top right by Wilkinson and others. And it's interesting to see in this gray bullet at the top that the idea of the FAIR principles was to ensure that data are shared in a way that enables and enhances reuse by humans and machines. And so there was a fairly strong focus on data. And as you can see in the principles under each of these letters, principles actually talk about what should be done with data, and they also should talk about what should be done with metadata. And in this kind of shorthand that's used of meta in parentheses data is often used in these principles to talk about things that apply to both metadata and data. And I'm not going to go into this in any detail because I'm guessing that people are probably familiar with the FAIR principles overall to begin with. And I think the key part of this is, again, is the fact that they're principles in order to make data findable, accessible, interoperable, and reusable, both by humans and machines. And then there's just a bunch of specific things that in an ideal world would happen that would make this true. So if we think about FAIR for non-data objects, such as, let's say, machine learning models as an example, we have the fact that the FAIR principles say in this paper that I pointed to on the last slide, says that the FAIR principles are intended to apply to all research objects, both those used in research and those that are research outputs. As I mentioned before, the text often says metadata, and that's shorthand for metadata and data. And if you read these and think about these, or if you've been involved, you realize that the principles are applied by two different groups. The dataset creators have to do some work to make their data fair, and then repositories also have to be involved to make the data fair. And so the creators and the repositories collectively are responsible for creating and annotating and indexing and preserving and sharing the data sets and their metadata. So if we think about non-data objects, again, machine learning models maybe as an example, software as an example, workflows as an example, all these things can be stored as data, but they're not just data. And the high-level goals of making them findable, accessible, interoperable, and reusable are mostly the same. But the details and how you can actually implement principles to make them fair depend on how the objects are created and used, how and where the objects are stored and shared, and how and where metadata is stored and indexed. And again, there are we've come to kind of ways of doing this for data, but we don't necessarily have the same ways that we do this for other kinds of objects. And so we believe then that there's work that's needed to define FAIR principles and then implement those principles and then get to widespread adoption of those principles, again, for objects that are not data, where a lot of this work has already happened for data. So it's worth, again, mentioning that here we're looking at the adaptation and adoption of the FAIR principles for machine learning, and the FAIR Practice Task Force under EOSC a year and a half ago put out a set of 6 recommendations, and the 5th one of those was to recognize that FAIR guidelines will require translation for other digital objects, and that such efforts should be supported. And so again, in Wilkinson's paper, there was the idea that the FAIR principles would just apply to all digital objects, but since then there's been the realization that this doesn't happen automatically, and that there's both translation work and other work that's needed to make this happen. So thinking about where this is actually happening, there's a bunch of different kinds of non-data objects that have had efforts in fairness. There was work on making training materials fair. There's work on making computational workflows fair. There's work on making research software fair, which I've been involved with. And then there's work on making virtual research environments or science gateways fair. And here we want to talk about machine learning and machine learning models. So as previously stated, the original FAIR principles claim to apply to scholarly digital research objects, but actually focus on metadata and data. The work in FAIR for research software and FAIR workflows is really focused on how to translate and interpret those principles for research software and for workflows. And so if we think about machine learning models, we can ask some questions. Are machine learning models data? So for example, you could think of them as a set of parameters and options for a particular framework. And if so, then maybe the data principles, the original FAIR principles for data apply. You could also say, are machine learning models software? You could say that potentially because you could think of a model as an executable object that takes input, acts on it, and provides output. And if so, then maybe the FAIR principles for software that are almost accepted by RDA and hopefully will be in another couple of months are the right thing to look at. Or maybe machine learning models are something else. Maybe they have some data aspects and some software aspects and some aspects that are different from both data and software. So that's kind of what we're looking at and what we're thinking about. If we think about how FAIR applies to machine learning models, we have, again, the fact that large elements of FAIR for data are dependent on archival repositories, things like Zenodo or other repositories that are in re3 data. And the reason for this is that these repositories hold the data and the metadata, and they then provide search and access capabilities. If we think about software as a kind of a counterexample, software typically isn't shared via archival repositories, but it's usually shared either through social coding platforms like GitHub or package management systems like PyPy or CRAN. And so how metadata exists in those platforms is quite different. How search is done is different. How access is done is different. And there's some, we wonder about machine learning models again here. And we could imagine that machine learning models maybe will be searched and shared via repositories like Zenodo. Maybe they'll be searched and shared via executable platforms. Maybe there will be some kind of Earthcube platform or some kind of ESIP platform or some kind of geo platform more generally. Or maybe they'll be searched and shared via something else, things like DL Hub, the deep learning hub from Argonne, or OpenML, that's a kind of European activity. And then we also have the fact that models and training data are really linked. Right? The model is dependent on its training data, and maybe they should be shared together. So how would we do this if the training data is in one place and the model's in another place? This is something where something like OpenML may be a good answer that allows you to share them both together. So we've been thinking about this again for a little over a year, kind of starting in late 2020. And we put in a poster at RDA Virtual Plenary 16. And the poster is the thing that's on the top right here, basically saying we think that there's a problem here and we want to investigate it. We had a BOF at the RDA Virtual Plenary 17 and got some people together and started talking about this a bit. And then we started doing a bit more work. We had a talk at the FAIR Festival in June of last year on FAIR for Machine Learning Models. We had a community call where we tried to bring together all the people that had been involved in any of the activities so far. We had a talk at ESIP summer meeting in July. We had a talk at a computer science, data science oriented meeting in October. We had some BOFs at a pair of BOFs at RDA's Virtual Plenary 18 in November of last year. And we had a BOF at the Supercomputing Conference also in November. Trying to bring in people on HPC that weren't really active in RDA as a new community. We have this talk, sorry, with the date wrong, should be the 19th, I'll fix that. And then next week, we're gonna have a second community call. And basically where we've gotten to at this point is being pretty strongly convinced that something is needed to bring people together. There's some people think a RDA working group is the right thing to do to focus on building principles. I think the majority of people think that an RDA interest group is probably a better thing to do at this point, to really bring a community together and have that community talk about different things that it needs to do. And those activities then could spin off into individual working groups. And part of the reason for this is that RDA working groups are 18-month and are intended to produce an output, whereas RDA interest groups can go on for a longer point and are really intended to be a meeting of people that just have a shared interest. So what we're hoping to do there is to make a decision on interest group or working group. I think it's going to be interest group, but it'll depend on who comes and what arguments get made. And then to identify co-chairs. So Fotis and I have been involved and potentially would be co-chairs, but the FAIR for Research Software Working Group had 9 co-chairs, and it was really actually very useful to have a much larger number. So we're looking for other people that want to lead at least part of an activity, maybe a working group, maybe part of the interest group. The last thing I want to say is that it's also pretty important for us to figure out who we need to bring into this community. And so we've started off with a group of relevant projects and stakeholders, and this has not expanded anywhere near as much as I thought it would. And so we're really interested in finding out about other groups that should also be brought into this. And if you have ideas on this, please contact me. If you're interested in co-leading an activity, please contact me. If you are interested in just getting details about the community call next week, contact me and I can send those as well. But just to briefly talk about this, we kind of think that there's 3 different aspects that we can look at: platforms, communities, and projects. Platforms, I already talked about DL Hub and OpenML as platforms that let you share, publish, run machine learning models. In some cases, also share data and work on how to make better models. Kipoi is an API and repository of models that's specific to genomics. We have communities like the Pistoia Alliance working in healthcare, Elixir, again, working in healthcare, and Clear, which is working in AI research. And then we have projects like FAIR for High Energy Physics project that I'm working on, an HPC FAIR that is looking at HPC and fairness there. And so again, we're looking for who else should we be bringing into a community that we hope we will be forming in the next months to come. I think that's all that I'm going to say. Yep, that looks like it. So I don't know what format we want to use for this, but if anybody has questions, we could talk now, or if we want to put things in the notes, that's fine. Or if you want to save this until after all the talks, that's fine as well. I'll be here for the full session. So thank you.
Thank you, Dan. I think we have time for questions. So anybody can pull out the Slido and read the question, because I don't have link. I cannot open the Kiko chat. So
I don't believe that we have a Slido set up for this session, but if people want to either use the reactions to raise hand, we can find people that way, or if people just want to unmute and ask questions. I see a hand from Rob Casey.
Thanks for this presentation, Dan. I really like that summary panel you had on early on in the talk, with the just kind of the brief outline of FAIR. With regards to ML models, I'm wondering, is it something that can be, to be fair, can they be served up black box without training data references, or do FAIR ML models depend on precise reproduction of training data, such that the training data itself would have to be extremely fair itself?
Yeah, I don't think we know the answer to that. I could argue it from both sides. So I think in the FAIR for High Energy Physics work that we're doing, it seems there that the models themselves are useful without the training data for people that just want to use the model. So for example, if we're looking at triggering based on events that are happening in a high energy physics experiment, if the triggering works, that's fine, and people are just happy to get that down selection of the I don't know, kind of 1 in 1,000 events that are triggered, that are really the interesting ones that occur, that are the interesting ones. But I could also see places where somebody's interest in the machine learning model is not merely in running it, but it's really in understanding it and adapting it and doing something else with it. So I don't think that we know the answer to that yet. Looks like there's a couple other questions. John Wu.
Yeah, thanks, Dan. I think at most the comments and I think you probably know the ML comments. They also trying to it's not exactly the same purpose, but they want to doing machine learning model performance evaluation and those things. So my question, comment is how do you see the connection between that community and the community you said? Thanks.
So I have to say, I actually don't know much about that community, so I'm not sure that I have a good answer to that. Maybe if in the Google Doc, if you could put in a link to that, that would be really helpful for me. Then we can follow up and try to see. I will say, okay, thanks. Let me.
Sure. Yeah, I'll put it there. Thanks.
Okay, great. Thank you. I was going to say that as I was realizing, I was kind of talking about this from my point of view, which has been this focus on sharing the models. And if we're thinking about sharing the models, there really are kind of these interesting questions about like what metadata do we need for models in order to make them findable and accessible and useful, as well as how do we actually do the sharing. And so I know that there's been some interesting work that's been going on in terms of thinking about like what are metadata standards that should apply to machine learning models. So that's one side. I don't know if that goes towards the ML Commons activity or not. Sorry,
yeah, not too much on the standard. I think they are more on an actual model, practices. Basically finding the best model among some problems. I think it's different to focus, but I think it's a large community now. It have a good industry and involvements, and including HPC, and I know HPC people there.
Okay, so, yeah, thank you. So I will look into that. And thanks also to Charles. I think that's also something interesting to think about there. The other thing that I was going to say is part of the discussion that's come up in some of the previous events has been there are some people that are interested in just potentially writing a white paper or writing a paper about FAIR within the machine learning context overall. And so that could be looking at how does FAIR apply to training machine learning models? How does FAIR apply to the data sets? So I think there's an interesting potential theme there that some people are interested in. And then sorry, there's one other thing that I was thinking about with this as well. Sorry, it's escaping me for the second, so maybe I'll let Seth say kind of what he wanted to say, and then I can come back and hopefully be reminded of what I was just going to say.
Sure. So I would argue that I think if we really care about reproducible, and in particular being able to reproduce research in the service of the ongoing confirmation of science, I think we have a duty to provide the training data in addition to the trained models. Because I think with machine learning, with statistics, there's always the problem of, did I overfit my data? And machine learning sort of takes that to an extreme of that, the garbage in, garbage out problem is so dangerous in machine learning because it's really easy to get a black box that produces pretty results that don't mean anything. That I think we have to at least most of the time try to make the training data available in addition to the model and the code. So yeah, that's
okay.
My position on that.
Okay. Yeah, and so thank you. So that leads into the thing that I was going to say that I had lost for a minute, which is that we've been thinking about FAIR, right? And FAIR is these 4 specific letters, 4 specific properties: findable, accessible, interoperable, and reusable. There are a huge number of other properties that are valuable for science and valuable for machine learning. So things related to ethics, for example, and bias. What our hope is to really keep a narrow focus on FAIR and to let other communities and other groups start to look at some of these other issues that are equally important. But just, I guess we kind of feel like we can't do everything, and we want to focus on one thing that we think we can do and let other groups focus on the other things. And so I think the comment that Seth is making is kind of falls into this very well, that for science to go forward, I completely agree that the data should also be fair, and in some sense, all data should be fair. And so the only question is that something that makes sense for us to try to address in a FAIR for machine learning models activity, or is it something that just already is happening within a different activity? So anyhow, but thanks. I completely appreciate what the point you're making. Okay, so and we're going to go on. Mike says to the next speaker. So thanks very much again.
Thank you, Dan. Thank you all the questions. And the next speaker is going to be Jim Wang from UMBC. Jim, take it away.
Yeah, I think you can see my screen now. I think thanks for Dan's first talk. I think he gave a big picture on what fairness for machine learning is, and also the question about talking about reproducibility. My background is computing, computer science, data science. So we are trying to address reproducibility perspective from a solution how we can do it. So this is our small toolkit and our ideas on that. So we have my students from my lab, and also we have a collaborator from GPL, and he will help us with applications in Earth Science. For the fairness challenge for AI and machine learning, one of the main challenge is reproducibility. As Dan said, so the machine learning models, they are not just the data. And for people who want to trust the results, many people want to reproduce it, because by reproducing existing experiments and get consistent results, we have more confidence of the model itself. But besides that, to reproduce the exact same thing, we also want to do how we can do it with different data sets. We were talking about biases in the data sets. Could we change the data sets a little bit and rerun the model and retrain the model to see a different results, and also different arguments, hyperparameters and other things, and environments. If you run on GPU or CPU, those things we would be different. We in this talk we focus on a cloud-based reproducibility, because we think it's a main approach to for reproducible computing services. The cloud gives us a lot of freedom to get the full stack of computational environments, including the hardware, software, data, and all could be provisioned and shared via various cloud services. And that's why our solution is built on the top of the cloud-based reproducibility. And we think also cloud is a major environment for the Earth Science community, because more and more data from NASA and other data providers, they plan to host the data in the clouds. And if you have data in the clouds, reproduce it, rather train the machine learning model in the clouds and reproduce it in the clouds will be very convenient. So our work is mostly on a small toolkit. We call it reproducible and portable big data analytics in the clouds. We call it RPAC. It's integrating serverless computing techniques and to enable automate end-to-end big data analytic pipelines. And we'll talk about some examples in later. And we, besides to make it reproducible, we also want to make it to be cloud agnostic. Basically, we have a vendor lock-in problem if you only do everything within one cloud. And what if other people only have, like, say, can only run on other clouds, how you can do it. So our toolkit supports both AWS and other cloud environments, and we think our model can support more than these two environments. And to make sure it works, and we tried with both CPU-based and GPU-based big data analytics and building our toolkit. So some background, I said a little bit already. So to me, reproducibility involved 4 different aspects. And the first one is how do you rerun exact same application? We have to know the result is the same if you re-execute everything the same. But besides it, if you try different configurations, different data sets, applications, and how the application perform with different data set arguments, and how you can run it with a different environment. For example, you run with more and more CPU or GPU machines, are able to get better performance. The last one, if you switch to a data provider, you switch from Amazon Web Service to Azure, and are you able to do it? That's the last part, reproducibility to us. In terms of clouds, our set the cloud provide a lot of advantages, and here we use one particular model they call serverless computing. It asks the provider to allocate resources and on demand, taking up the servers on behalf of their customers. Basically, you don't need to host a server continuously. You just when you use the cloud whenever you need it, and what it give you is that you can request the services without maintaining backend servers. Besides that, it also employs the function as a service. It allows the customer to develop a separate function directly instead of standalone cloud applications. It's basically have we then talk about the workflow. So this here through the service computing and the function as a service, it can build a pipeline, and you can have individual service individual functions there, and they are linked together through internal and external events. So this is overview of our small toolkit, and the figure shows on the right. So it enables either rerun previous experiments with the same and different setup. You can see here at the beginning, you run it at the first time, and there's 4 different reproduction, as I mentioned a moment ago. And on the right is how it can be done. It's basically utilize the serverless-based pipeline execution and to provide the hardware environments to provision the software environments and run experiments with model training and testing, and eventually we store the information to save it in a cloud storage. In later on, other people will be able to pick it up and rerun it. And eventually, we have to terminate the resources. So to make it, I think 2 part of our toolkit is that we make everything automated, and with single commands, you can rerun the whole experiments and the whole pipeline and with only 1 command. So because the user sometimes they started like the watch cloud instance and they forgot to terminate it, and it will keep charging you unless you terminate it. The second part of our toolkit is we really want a minimum information requirement from the users. Because writing the pipeline, those things directly, it's very painful. You have to know the templates, the specification for those JSON pipelines. We only require them for the minimum information, like what are the personal information to be able to use your clouds. What is the clouds instances you want to use, and where is your program they can download, where is the input data they can train the model. So move on a little bit on the to first execution. We provide these 3 types of configuration. There's just a text file you edit there, provide your information, and then our toolkit will create a pipeline for the target clouds, and we run it in the clouds and save the clouds, save the results in the storage, so other people will be able to reproduce it. To reproduce it, we said I have this 3 approach. If you only run with same configuration, same environment, you only need to provide your own, say, cloud credential, so you can run the same thing in the same environment. If you want to change something, you want to change the different data sets. No, this is different environments. For example, different virtual machines, you can change 1 more configuration file, and then it will run the same model, same data sets, just in a different, for example, a more powerful virtual machine, or maybe more virtual machines. And also you can change it to be change the application part. You want to change it with different data sets, or you change the model a little bit, and then want to see the results. The last part is you want to run the same thing, but in a different environment. From a user perspective, as long as I know the data, I have my machine learning model, I should be able to run on a different clouds. So what this toolkit need to do is to be able to know how to provide the functions for the target clouds and the service mapping between the clouds. The service you have from Amazon Web Service, how we can map to the other services. We also support a few different big data analytics, and I don't need have time to explain every part, but we support like different multiple virtual CPU-based executions through Spark and Dask, and also with multiple GPU-based execution through Hello World. That's the big data parts and scalability part we support right now. To adopt it apply it in Earth Science, we have 2 applications right now. The first one is called property retrieval. It's using a random forest machine learning model to retrieve the cloud mask and cloud face from the various and Calliope satellite observations. And the second one is ocean ID identification. We use a CNN and YOLO deep learning model to detect the whether this image satellite data set has the ocean ID and where is the ocean ID. So this is a little bit on the ocean ID application. I think Jimbo will talk about this more in moments. Here we just want to say it's what we show as examples of the ocean IDs, and they are from the SAR data and others. And they will be in the next big mission from NASA, the called SWOT. we hopefully machine learning can play a big role to automatically extract data from very large amount of data sets. So coming back to the fairness requirement for this particular application, why we think this how to make it fair and reproducible. So first one is how to make the training data set fair, and well, the part we think is very important is doing labeling, because for the Ocean ID, where is the ID, and that will determine how well is the model tremendously. So we are exploring everything through the clouds. For the data training, we are exploring SageMaker to access data from AWS, and they can support collaborative labeling. But we have some difficulty to directly load the data from the clouds to the SageMaker, especially the formats we have, like the TIFF file and NetCDF is not that easy, can be loaded to the SageMaker right now. The second part is how to record the model and train the whole training process for user reproducibility. If you have the model, other people can be able to retrain it. And the toolkit I mentioned a little bit ago, that can help automate the training and later on to reproduce it. The next part is to iteratively improve the Ocean ID capabilities through the collaborative efforts. Because when someone have the first results, the community will always want to say, could we make the model better? So the cloud services and the toolkit I mentioned a little bit, they can provide others be able to add additional data sets, the training data sets for better model accuracy, or just build a better training model. You know, right now deep learning model and get more and more complicated. Maybe we can get a better model for the Ocean ID detection. So as a conclusion part, we think of using serverless containerization and particular design pattern we used for achieve the cross clouds reproducibility, and we tried it with multiple applications with distributed environment in the cloud. We are applying the toolkit with Earth and applications, and to know more about this toolkit, is we have a link here, and also this afternoon we have a toolkit demo in the research showcase post and demo. That's 4:30 to 6 Eastern time today. So I will be there if you want to know more about our toolkits. And we acknowledge the grant support from NSF, NASA, and ARL, and ESIP. Thanks.
Thank you, Jianwu. I think we don't have time for questions, so feel free to type your question in the chat. And then let's go to Jimbo. Jimbo, can you share the screen?
Yes, thanks. Let me share my screen. Can you see my screen, Jensen?
Yeah.
Okay, great. Let me turn on my video. Okay, thanks, Jensen, for inviting me to this. My background is earth science, oceanography. So my talk is a little bit from a different angle, from another side of the discipline that we want to apply machine learning to some science use case. My talk title is Fair Through Podak Cloud. I'm Jimbo Wang. I have a lot of collaborators listed here. I will not go through all the names, but from JPL and also Jianwu and Siraj from UMBC and Jensen from GMU. So I want also acknowledge that the support by STSWG, ESIP, and NASA PO program. So first of all, let me briefly introduce Podak. I'm the project scientist for Podak. Podak is one of the distributed active archive center of NASA Earth Observing System Data Information System, aka EOS DIS data center. It is managed by Earth Science Data Information System as this product. It is operated by JPL in Pasadena. So the mission of Podak is to preserve NASA's ocean climate data and make them universally accessible and meaningful. So in addition to providing access to the data holdings, Podak also acts as a gateway to data stored at other ocean climate archives. And these other tools and services enable Podak to support a wide user community working in the areas such as ocean and climate research, applied science in the industry, natural resource management, policymaking, and the general public consumption. With this, we have a huge amount of data, including more than 20 large NASA missions, as well as a PI-generated data product. This fits into the first part of FAIR, is findable and accessible. So we have been doing this since early 1980s. So this is a brief introduction of the Podak. Now I want to switch gear to the physics, the ocean turbulence. Let me play this animation. Then the ocean circulation is highly turbulent, as we see from this animation. It was made 10 years ago based on an ocean data assimilation product called ECHO. So the wide circular movement is the particle trajectories produced by the transport of surface velocity. The trace of them illuminates the ocean circulation. The circulation, as you can see, is very turbulent, full of circular structures that we call eddies. So the structure of the eddies, you can see from this animation, has diameter larger than 100 kilometers. It can be seen by existing satellite altimeters, such as the Sentinel-6, Michael Froelich, and Jason-3. But ocean circulation at smaller scales are important in transporting the water and tracers between the ocean surface and the ocean interior, but they are not resolvable by the current model or remote sensing technology. The numerical simulation nowadays can resolve the global ocean features with a horizontal scale down to order of 10 kilometers. This is a big animation. I'm not sure whether you see it or it's just a totally blur. If you can see that, that the ocean is full of small scale eddies that otherwise does not exist in low resolution models or low resolution satellite images. This particular animation shows the surface relative vorticity from ECHO product when 48th degree simulation. The horizontal gray size is about 2 kilometers in the global ocean. And these small scale eddies has diameter about on the order of 10 kilometers, as Jian Wu illustrated in his talk. They will be resolved by the new satellite mission, the Surface Water and Ocean Topography mission, so-called SWOT, S-W-O-T. Now, high resolution remote sensing obviously leads to a large amount of data. SWOT will produce 20 terabyte a day data, and they will go directly to Podak Cloud, which is NASA Earth's data cloud hosted on AWS. With these large amounts of data, we need to build a cloud native environment to bring code to the data rather than download the data to a computer and analyze locally. And also, we also need tools such as machine learning to extract useful information from this huge amount of data. So we have been developing tools and demonstrations among these two lines, and with collaborations with Jian Wu and Jason. So on the topic of FAIR, Podak has been hosting NASA mission for 30 years. So all the machineries and pipelines and how we ingest the data and validate the data has established a very robust pathway to generate the data that is findable and accessible and self-explanatory with the necessary meta information. So the tools for search, discovery, visualization, transformation has been available for on-premise and also cloud-based data after recent development. So we decided to move all the data to a cloud because with SWOT, this large amount of data from SWOT really make us think that we need to move to the cloud rather than purchasing hardware for local storage. So it will further enable findable and accessible elements of FAIR. So as of December of last year, we have migrated about 400 terabytes of data to cloud, which includes 150 data sets and nearly 14 million files. We are on the target to complete data migration to cloud by June this year. The recent the satellite mission Sentinel-6 microflight was the first NASA mission in the cloud, directly in the cloud. SWOT will be the next one. It will be launched in November this year. Will be a big task for us. So this is two pilot studies. The second element of FAIR, interoperable and reusable. Right. This is the first pilot study is a collaboration with Jian Wen and his group. The goal is to establish database on small-scale ocean features based on SAR images and high-resolution satellite sea surface temperature. From the very beginning, we are thinking of FAIR. We want to build this line work based on cloud and make all the code transparent. I will not show the results, but just one identified pain point for accomplishing FAIR in this case is the lack of a robust cloud-based platform for labeling geoscience images. Basically, keep the latitude and longitude and all other metadata that you need to geoscience. I think Jian Wu also mentioned this point. So just quickly for the second pilot study, this is in collaboration with Jensen. The target is to build a cloud-native machine learning pipeline for detecting ocean eddies. We took 3 steps. First, we built a training database based on an open source tool, which is called a Pi Eddy Tracker. It's open source, we can download and we can go through the steps and apply to the example files and also to the files and data that hosted in Podak cloud. The second step, we train this model based on local machine with a limited number of training data set. And then the third step is to apply this trained model to Podak data and directly run this in the AWS environment. The second and third steps are all in progress. But here is just a quickly an illustration of what we are doing. On the bottom left is the Pi Eddy Tracker generated training data set. Each yellow or blue dots are marked eddy positions and the size. You can look at the size by counting the area. On the right-hand side is a preliminary result of our machine learning-based algorithm. On the left column is the satellite image, graded product, L4 product, level 4 product. The middle column is the training data set. And the right column is the machine learning-based eddy identification. It's workable, it's okay with large eddies, but you can see the difference is still there. We will continue to test this with a larger training data set and increase the accuracy. So with that, I will conclude. I want to conclude with 3 points. So Podak has established a very robust workflow to enable the first element of FAIR, right? Findable and accessible, and keeping all the metadata and a rigorous vetting of the metadata has been our focus. The second is that cloud-based machine learning pipeline will reduce the research duplication, increase reproducibility, and facilitate open science. This is directly related to the second element of FAIR. The third one I want to emphasize is through this collaboration really facilitated by the SSWG and ACIP, We have experienced early exposure to the machine learning tools such as Genwoo's RPAC, and this kind of early collaboration will ease the future technology adoption, make it more, make it smoother to
Thank you so much, Will. That's a very nice work, and I look forward to get something done in this new year. And I think we don't have time for questions, so we probably leave all these questions either in the chat or we can circle back in the end if we had time. Next speaker is going to be our community fellow, Michael.
Yeah, thank you. Let
Yeah,
me,
take it away.
I've got a million tabs open. Let me get the one that I'm looking for. There we go. All right, so hopefully that's showing up for everyone. So,
Looks good.
awesome. Well, hi everyone, and thank you so much for coming to our session. And I'm really excited to talk to you all today about how we're using AI and machine learning to help New York State hit its net zero carbon goals. But before I get started, I should probably introduce myself. I'm Mike Mahoney, and I'm currently a PhD student at the State University of New York College of Environmental Science and Forestry, as well as one of this year's ESIP Community Fellows working with the machine learning cluster. My work focuses on ways to help people understand large-scale systems, especially when it comes to land use and forest ecology over time. And the work I'm talking about today is all part of that through my role with ESF's Climate and Applied Forest Research Institute. So, back in 2019, New York State signed its landmark climate bill, the Climate Leadership and Community Protection Act, into law. That bill does a lot of things, but in particular, it mandates that the state needs to hit net zero emissions statewide by 2050. In order to meet that goal, New York is working on reducing its greenhouse gas emissions across all sectors, but that's only going to get us about 85% of the way there. The last component of hitting net zero is going to require managing land across the state to capture and sequester carbon for years to come. And in particular, we're really going to depend on forest lands to work as carbon sinks. But in order for us to rely on forest lands, we need to know how much carbon is actually being captured by forests across the state. We also need a way to monitor that carbon storage over time and to prioritize any efforts by the state to conserve and reforest land in order to capture more carbon. But up until recently, we've had very limited ability to actually answer these questions. You see, our main insight into the state of New York forests comes from the USDA's Forest Inventory Analysis Program, or FIA. The FIA has over 6,000 plots around New York State, which we can use to get point estimates of forest structure. But while the FIA is a fantastic, irreplaceable resource, it's a national forest inventory that's been going strong since 1930. Just like any other data source, the FIA has some challenges. For instance, the FIA only really measures interior forests, and it doesn't go out and measure the sort of marginal forest and mixed-use landscape that makes up a lot of New York. They also measure relatively small plots with large spaces between them, which means that FIA estimates have to be pretty broad scale, which makes them hard to use to identify important areas for conservation and reforestation. Each plot is also only measured once every 5 years, making it hard to see short-term changes in the landscape and respond quickly. And again, FIA is pretty much best in class for forest measurement. It is prohibitively expensive to actually go out and measure a more dense forest inventory than this. And so we're stuck with that old Peter Drucker quote, if you can't measure it, you can't manage it. If New York wants to manage its lands to help it reach net zero carbon, we need to find a better way to track how much carbon is actually being stored in its land. And so that's where our work comes in. The core question of our work is how can we use remote sensing data and machine learning to try and fill in those measurement gaps? And so on the remote sensing end of the question, one thing that New York has going for it is that we have a good amount of high resolution airborne LiDAR data available for us to work with. In particular, since 2014, a number of groups, especially FEMA and the USGS, have produced high quality publicly available LiDAR that we can use to try and get a sense of forest structure across the state. Of course, these data sets don't all represent the same set conditions. A lot has changed from 2014 to 2020, and there's a lot of the state that we don't have LiDAR data for at all. So what we do in our group is take advantage of this LiDAR where it exists to generate point-in-time snapshots of New York's forest lands, and then use models fit on spaceborne remote sensing data, especially from Landsat, to extrapolate outside of those spatiotemporal extents. And so what I want to focus on today is to talk about how we've applied that approach to those key questions I mentioned, to try and track how much carbon is being captured by forests across the state and to try and prioritize conservation efforts. So I want to start off talking about how we track how much carbon is stored in forests across the state. And to reiterate, the FIA is hands down our best resource for actually measuring how much carbon is stored in a forest. Now, the way that the FIA lays out their subplot or their plots is a little bit wonky. An FIA plot is actually a set of 4 disconnected subplots, which on this diagram are the circles with the lines connecting their centers. And so inside of those subplot boundaries, the FIA measures every tree, records its height and diameter, which we can then, through some standard equations, convert into the biomass of the tree, which you can then go on to convert into the actual amount of carbon that the tree is storing in its wood fibers. And so what we do is we take those plot level biomass estimates and associate them with the airborne LiDAR point clouds. We can then calculate a number of metrics from the LiDAR point clouds and then use them to fit machine learning models. And so for this project, we fit a random forest gradient boosting machine and support vector machine to the data from those FIA plots. We then use each of those models to predict a validation data set, then use those predictions to fit a simple linear regression model that combines those machine learning approaches into a single prediction. That ensembling step gives us a lot of freedom to make changes to the individual machine learning methods. If we accidentally make one model much less predictive, it gets downweighted in the ensemble and the other 2 models pick up the slack. And we've consistently seen that the ensemble model is more accurate than any of the individual component models. And so we take that final ensemble model and predict biomass on a 30-meter grid for all of the years and areas that we have LiDAR. Now, I'm not going to dive too deeply into our assessment protocol for these maps, but I want to highlight that we make a point of assessing our map accuracy aggregated to multiple different scales. And what we find is that our predictions are pretty accurate at even the finest scales we investigate, with R-squareds ranging from like 76 to 81%. And while this is less of a formal result, we also were recently told by a stakeholder at the Nature Conservancy that predictions are between 90 and 99% accurate to their own field measurements. So we then move on to the second part of our framework, where we're using spaceborne remote sensing data to start extrapolating beyond the reach of our LiDAR data. And so we retrain our models using the predictions from our LiDAR surfaces and produce new models that can predict biomass across the entire state. We can then use those models to generate predictions for every year from 1990 to 2019, which is the span that we have FIA data to compare against, and then assess those using the same multiple scale protocol as the LiDAR maps. And so we're able to use these maps to get a sense of how the amount of carbon stored in forests across the state change over time. We can start to fill in those measurement gaps so we can start managing our lands to maximize carbon storage across the state. And now, one very cool thing about having these fine scale time series is that they let us detect all sorts of changes in forest structure that we can't pick up based on FIA measurements alone. So for instance, this is a map showing our predictions around an area that was cut in 2018. So more green here represents more biomass. And you can see that our models between 2017 on top and 2019 on the bottom pick up pretty strongly on the harvest that happened inside of those lines, even though the surrounding area doesn't really change. And so through these time series, we can get a much better sense of forest management activities that are happening than we can get from using FIA plot data alone. And so to move on to the other place we're applying this same framework, we're also engaged in trying to prioritize the state's reforestation efforts, areas to protect and maybe even plant to promote more carbon storage. Now, there's a lot of very smart and defensible opinions on how the state should go about prioritizing reforestation. Without going too far into them, one possible method would be to prioritize conserving areas that are already reforesting on their own. So abandoned fields and young forests that will develop into productive forests without needing any planting or help from the state. And so what we've done is apply the same framework of moving from individual point-in-time snapshots based on LiDAR data into statewide predictions based upon remote sensing from space. The challenge here is that the FIA only measures interior forest lands, so we don't have a great validation data set to compare our models against. So what we've done is take one of the leading land cover classification products, LCMAP, to try and identify vegetated areas across the state and remove non-vegetated lands from our maps. We then combine that with our LiDAR data to identify areas that are between 1 and 5 meters tall, which is in line with what NLCD calls shrubland. And whether we think of this as being shrubland or young forest or areas that seem to have short vegetation based on remote sensing, these are areas that are probably promising candidates for reforestation. And in total, we find that the areas we have LiDAR for are about 2.5% shrubland. Now, something to highlight here is that this surface is not a machine learning output. We're able to classify all of the area covered by LiDAR without needing to fit models. So we can skip the step where we fit models to the airborne LiDAR data and instead move right along to extrapolating beyond these areas using spaceborne remote sensing data. And so just like before, we fit an ensemble model, this time swapping out the support vector machine for a neural net. And we can then go ahead and predict the areas covered by LiDAR for the years that we have LiDAR data in order to assess our model accuracy. And we find that with this approach, our predictions are pretty good. We have an AUC, for instance, of 0.89. And so we can go ahead and use the same models to extrapolate our predictions to the rest of the state. So this is the 2019 prediction surface. Now, one challenge with this approach is that because shrubland is so rare across the state, even a low level of false positives will translate into a large absolute number of false positive predictions. So what we do is identify a number of classification thresholds that we can use to actually classify those predictions, raising the bar required to consider a pixel shrubland to try and reduce false positives overall. So we're able to offer multiple products that are tuned to a stakeholder's tolerance for false positive predictions. And so that's a quick overview of some of the ways New York is trying to use AI and machine learning to fill in some of its measurement gaps when it comes to forest structure to try and manage for a net zero carbon future. But I want to wrap up today by connecting these projects directly to the theme of our session on fairness in machine learning. So I hope I've made it clear that we're engaged in a lot of data-intensive projects to try and help New York fill in measurement gaps and manage its forest lands. And one of our largest challenges as a data-intensive team is figuring out how we can integrate new data streams into our workflows. We maintain a central data mart for our research group, where we store a set of standardized, pre-processed, and validated data for use in our models. Every time we add a product to that set, we're also adding a commitment for our small team to track updates to that data product and to reprocess and upload the data on our end should anything change. There's a world in which all of our data sources are publishing sufficient human and machine readable metadata that we can automate that burden away. But right now, it's a serious obstacle to incorporating new products into our workflow. In the other direction, we also are a producer of data products, and we're still in the process of figuring out how we can release our data in a format that best serves all our stakeholders. Open data and open science often prioritize those who know how to code and how to decode scientific jargon to the exclusion of everyone else. And that's not a good place to be if we're producing data products that are being used in management decisions that impact the lives of people across the state. Most people can't grab data from an API and have no idea how to read XML. So we need to find a way that we can make this information actually useful and usable for everyone who needs it or might be impacted by it. And so on that note, I want to thank you so much for your time. If you want, you can find me at Mike Mahoney 218 on most platforms or at my website, mm218.dev. Thanks.
Thank you so much, Mike. That was a very good, great presentation, actually. Very solid work and never misspell a word. Very impressive. Actually, I have tons of questions about fairness of this work, and probably we can talk offline. We have to move on to the next speaker is Nora. So I will pull up the slides first. Okay, I'm gonna share the second. Okay, can you see?
Yes, I see it.
Okay.
Okay. So my name is Laura Sandoval. I am a software engineer at the Laboratory for Atmospheric and Space Physics, so LASP at CU Boulder. I'm involved in pipeline development, data management, and data collaboration for various satellite missions. My colleague Jinsing and I led task 2 of the NASA Earth Science Data Working Group. And our task was to publish a paper in which we reviewed artificial intelligence in the field of Earth science data systems. So we had numerous experts, which I list in the acknowledgement section, who contributed to this paper. And I have just been given the privilege of presenting their work here today. Next slide. So here is an outline of our paper, and as you can see, it's quite extensive. It has a wealth of information, including a review of AI techniques, existing Earth AI research, machine learning workflow, and also tooling and services that are recommended for the field, And so I recommend going to our paper once it's published in the Computers and Geosciences and looking into it. However, for the scope of what we're talking about today, I am focusing on the challenges and opportunities that were discussed from the working group. So next slide. So this is a table from that paper that lists all of the Earth spheres that were covered. And the parentheses include the number of research topics. The AI techniques are in the second column. And then the research topics are shown on the right. So you can see that the majority of the machine learning research that is done right now is deep learning or artificial neural networks, which implies that the fields are moving towards very large data sets and more complicated models. Thought that was interesting. Next slide. Here is a figure taken from the paper in which the machine learning workflow is illustrated. And of course, this is in reality, this is an iterative process. The majority of the challenges and opportunities of the working group focused on the latter 3 steps, which are model development, deployment and maintenance, and integration and decision-making. So that's what I'll be talking about mostly. Next slide. So the first challenge that the working group realized was that of model development, or the process of choosing a suitable model. And they had concluded that this, in their experience, is very time consuming. For example, there's no generic approach to select an optimal set of layers for a neural network. A common approach is usually to implement a rough guess based on either experience, or if you're more new to the field, a training course, a blog, or a research paper. So the working group found that there were opportunities despite this obstacle, and made some recommendations. For example, data exploration prior to selecting the model can provide a baseline for an expectation of accuracy. And also a promising technology is AutoML. So of course, a good AutoML technology would find an optimal model solution easily and quickly, and that would reduce the barrier of shopping around for different machine learning models. However, current AutoML technologies available are not ideal. There were a number of issues that they found. For example, accuracy was assessed, but not stability, reliability, or computational cost. They found that AutoML performed poorly on big training data, and also it doesn't account for various use cases. So an opportunity here would be that a more developed AutoML technology could be useful in the future. To the next slide. And of course, as we've mentioned multiple times in this conference before, data preparation is a big barrier. Some of the challenges that the working group had discussed were time series. For example, from Earth observations, time series usually contain data gaps and noise. Some of the things that could help those problems would be bandpass filtering, upsampling, downsampling, detrending, interpolation, and smoothing. They also said that format is a big barrier. For example, every provider has its own format. NASA has HDF, NOAA has NetCDF, or GeoTIFF, depending on what source you're getting the data from. And even each format has various versions. So keeping up with those versions can be also very time consuming. They also said that multi-source data sets use various coordinate systems and require tedious processing, reprojection or gridding, and also metadata like naming conventions, variable units, resolution file version are often missing. And so an opportunity in this, in data preparation would be more effort on standardized data sets. Next slide. So another challenge that the working group found was training optimization, in which hyperparameters are adjusted to minimize the cost function. So optimizers are algorithms for changing the attributes, such as weighting. All optimization methods currently available have flaws. One common challenge of gradient-based optimizers is that most found minimum points or minimum points are local minimum instead of finding the global minimum, which are harder to locate. So there's really not a one size for all method that can adapt to any data set and speed up the learning to reach the minimum faster. So one opportunity in that category would be to improve the optimizer algorithm. Okay, next slide. And then parallel computing is valuable in Earth AI. One of the first reasons is that there is an ever increasing data volume available for Earth data. For example, climate data is expected to increase from by threefold from 2020 to 2030. The second reason is that there's increased complexity in the AI models, especially deep learning models. So the first opportunity that the working group realized is the potential for a unified system combining parallel hyperparameter tuning and parallel deep model training, which are currently performed via different systems. The second opportunity is the support for parallel learning on top of array-based Earth system data sets, including HDF and NetCDF. So Xarray and Dask are recent community efforts on assessing and processing HDF and NetCDF datasets efficiently, but it is still not clear how to integrate these techniques with machine learning. Next slide. And of course, explainable AI was one of the technologies that was discussed. When you use the deep learning models or neural networks, the complex models can't provide a explainable theory for the results often. So, you have all of these black box models, and scientists sometimes have a difficulty accepting the results. So one opportunity is explainable AI. So I put a picture here of one of the technologies that is available, which is LIME, which stands for Local Interpretable Model Agnostic Explanations. And what these explainable AI technologies do is they provide a qualitative understanding of relationships between model features and the predictions. They can explain what features are most important, and also any artifacts that create errors in the model could be revealed by explainable AI. So for example, an example of this would be, there have been machine learning models that have tried to identify what a cowboy looks like. And when you run the explainable AI software, you realize that the software is focusing more on the background than they are the actual cowboy. So is that something that the machine learning model should be doing? It's really up to the human to decide at that point. Okay, next slide. And also another common obstacle is generalization. So you can have an underfitted model or an overfitted model, whenever you're having these machine learning models. So the challenge would be to empirically trained models often do not generalize well on new samples with different distributions. So the deep learning models can use the noise rather than focusing on what they're supposed to be learning in order to overfit the data, for example. One opportunity would be to just simply apply the classic method to detect under overfitting. So you can do this by comparing the accuracy of the model using training and testing data sets. Or there's also the technique of regularization, which is reducing the impact of the noise so that they aren't affecting the model. And a future solution would be there's a potential to create an automatic algorithm that would self-adjust in adopting samples by judging their quality. Next slide. Another challenge is uncertainty quantification. So there's two different types of uncertainty. There's the uncertainty from the data, and then there's the uncertainty from the inadequate knowledge of the model. And so the data to reduce, let's see, to quantify estimate the uncertainty of all inputted data and understand how the uncertainty propagates. And that's challenging in deep learning because there's a high model complexity. So to understand how the uncertainty propagates is a challenge. And then related to generalization, which we discussed before, the model may not easily generalize to other conditions that are not covered in the original data set. So the opportunity is to use some common uncertainty quantifications, including Bayesian and ensemble uncertainty quantifications. Next slide. Provenance, reproducibility, replicability, and reusability were also discussed in the paper. So provenance, where did the training data, AI model, software, and hardware originate from? And what transformations have the data undergone before the findings were reported? Reproducibility, I think we all know that, can an independent party reproduce what you've done? Replicability would be if an independent party can run similar machine learning analysis and come up with the same conclusions. And then of course, reusability, we know that. So next slide. So some of the opportunities that they found were proposing standards for the data and scientific workflows. Also, software can be used to record the AI workflow, which I had never heard of this, but that was, you can use Docker, Helm, and Conda in order to record the AI workflow. So something to look into if you're interested in doing that. Also, simple solutions such as archiving data and storing that data into a repo and providing templates and tools so that people could go back and replicate your work was also a suggestion. Next slide. And then another challenge was putting the machine learning into a production environment. So using DevOps methods to make your machine learning production level ready. So this is something that will be discussed a little bit more. So there's ongoing projects. The GeoWeaver is one of them that is being worked on to deliver practical, stable software. And there's also a number of automated workflow software that are available. Next slide. So in summary, this group worked very hard to address the challenges and opportunities. And there was an emphasis on community experiences or in fairness of AI in that section of the paper. So next slide. Here's the author list of all of the people that contributed and did some really fantastic work. And we also wanted to give thanks to the working group, ESIP, who have provided their valuable time, advice, and editing work during writing this paper. So now I'll turn it over to Jinsing.
Thank you so much, Nora. It's open access paper, so everybody should have access if you know the URL. I believe somebody already put it in the chat. I cannot see it. So I'm gonna wrap up the session in maybe 8 minutes talk. Actually, I have a lot of things to talk about. Yes, as Nora said, that we have put a lot of effort into this paper, and we identified 12 challenges, but do not separate, isolate one of those challenges, because if you actually do something about one of them, all the other challenges, maybe opportunities will be impacted. So it's a whole package. It's like there is a chain reaction in there. So what we are trying to do here in ESIP is we have several ongoing activities. So first one, we already finished that, the review paper on what's going on in the earth science, like AI in earth science. We actually call that Earth AI because we are imagining that this is going to be a huge combination of systems. It's not like an abstract concept or something. It should be a system that can be used by everybody, like our weather forecasting system. It should be one part of it. And this Earth AI is going to be it's going to do some very amazing stuff, like protecting Earth from the geohazards or something like that. But how to achieve that, to go there, we have to use some right tools. Like every job has to use some right tool, and we are offering this GeoWeaver as one of them, because we have worked on this for 3 years now. So it finally has a 1.0 version. It's still alpha testing phase, and we have believed that it's going to be reached to the final stable version this year, maybe in several months. So why we do GeoWeaver here? Because daily research utility tool is key to make the AI fair and scientifically objective. We are trying to eliminate the human intervention from the AI workflow. And for students or scientists, when you are initially prototyping your research, actually all the other tools are not very useful in the early stage. I mean, like some benchmark tools that designed for the production environment, which is too heavy for you to do that. Actually, we only need two things in GeoWeaver to help the scientists to make the AI research either practical or bearable. Like first one is make it organized, because people are really messed up with the ML experiment right now, because we heard a lot about the ML models, but we didn't see much of the real model file or either the history. The provenance is not there at all. And so we try to use this tool to save and share the model run history. Model run history is different from the model or from the data. Model run history is some log file that has to be shared with the source code as well. But why choose GeoWeaver? Because we have like 1,000 of workflow management software already. Why another one, right? I have given this talk in the AGU town hall actually, so I'm not gonna repeat that, because there is a lot of gaps in the current workflow management software yet. So I don't know how many of you have actually used one of them, except those in the production level, in the companies, people are using them a lot. Actually, all these workflow management software are their backbone software. Everybody is working around that, checking those logs and fixing those bugs on the workflow management software. No, that is like their business like a business baseline or something. So, but it's not usable for scientists especially at early stage, like the students or researchers, postdoc, or even actually the data scientists working in NASA DAC, because it's too complicated and heavyweight, and it requires you to coding extra. That is extremely painful for people who just learn Python and only learn some packages doing the AML stuff. And also, there is no easy way out. If you created one workflow using one software, there is no easy way out. You have to stick with it for maybe many years, because if you want to switch software, you have to redo the whole thing. So GeoWeaver is like, it aims at some scientists affordable, either on time or monetary cost. First of all, it can preserve AI prevalence automatically. You don't have to do anything else. Just feed all your existing source code in there and run that, and GeoWeaver will do everything else for you. And it feels really good to have some tool backing you up. Especially when you're doing the AML, which every model run is different. That thanks to the random number generator algorithm in there. And it can automate your full stack workflow. Actually, you can chain everything like a shell script, and Python code, notebooks in a workflow pipeline. It has no string and no user tracing in the hassle-free, so you can feel free to remove it at any time. The workflow created in the GeoWeaver, you can open it and share it and run it even without GeoWeaver installed. This is the interface. Actually, I plan to do a small demo, but I don't know if I have time. We actually have some cluster plan. I mean, the ECF machine learning cluster are actively working on things like papers and experiments and the collaboration, training scientists, community members to use the AML in their research, because most people are really interested in that. Cross cluster, as Jimbo or Jim said, we're gonna do the Ocean 80s in this year, and actually we are collaborating with Ag and the climate cluster and disaster cluster on the wildfire. I actually have a lot of talk this afternoon on wildfire. I'm not a wildfire expert actually. I'm gonna talk anyway. So we're gonna collaborate with Reading Earth because this is backed by the NASA Access project, and we have the access. This is another access project on the crop mapping workflow, and Hamid already published the source code. We're gonna replicate that one in GeoWeaver and publish it again and see how it works. Because that GeoWeaver one will have history. So you even do not have to rerun the whole thing. You can see the history and then you say, okay, so this is credible. And all the evidence, this model actually has been run successfully before. So you have faith in the model result, like the crop maps or something. This is a white paper we are working on. So everybody is welcome to contribute, actually. We have the white paper for the practical AI because most people are not practically using AI, actually. The AI product is mostly prototype. And we have this repository, GitHub repository about awesome Earth AI, just pouring all these amazing tools and the videos into this GitHub repository so more people can see it and learn from it. We have a very good amount of stars and forks, so we really hope that the community can engage and contribute to this effort. So this is how to get involved with machine learning cluster. I'm not sure I have time. Yeah, we are 1 minute over. So I'm gonna take 1 minute to show you how the GeoWeaver looks like. So GeoWeaver is like this. So you can install it using the GDK or Docker. It's available in the Docker Hub. You can Docker pull GeoWeaver, and then it's on your machine. You can just start it. All these tutorials are there. So its GitHub repository is here. Actually, it has the CI/CD set up, the Circle CI, and every push, every commit, it has to be success. And you can check its code coverage here. It actually has 33, which is not very impressive. We're gonna improve that test suite coverage to make this software really robust for everybody to use. And I actually I can show you how to make it reusable. You know, if you create some workflows like this one and put all the Python code here. Oh, sorry, not here. I actually did a lot on this one. So I collaborated the source code from the SlowX, and this is a download or searching the CMI for the NSIDC dataset. So I just run it. It's gonna be very similar to what you do on the other environment, like IDE. So you can see I can search all this data from the CMI Earth data, nasa.gov, and then I can download it to my local machine. Yeah, I hope this is going to be a long demo. I don't have much time, so just a small demo. It's downloading data from SIDC, and it's successfully downloaded. And I can compose them into a workflow like this one, and I can run them together like this. So the deal is here. There is twofold, and like you can download the workflow using this button. And see, you have the entire thing on your laptop right now. If you open that, it's going to be a zip file, and it has code and history. So if you copy this to some GitHub repository, let's see. This is what I yeah, and then commit this one to the GitHub. So your source code and your history will be both preserved in the GitHub, and then you can publish it in the net or something. So this is going to make the entire workflow more reusable, we think, and because it has history, it will be more credible to believe. So that's a small demo. If you want to know more details, then come to our research showcase this night. Thank you so much. I think we are over time. Annie?
We are over time just by 5 minutes, so that's not too bad. There is a 1 hour break now until the next session. So if anyone did have time to stick around and ask any questions, I would certainly encourage you to do so. But if you need to take a break, stretch your legs, or just do some other work for a bit, we certainly understand. So with that, I will stop the recording and say thank you so much. But if anyone would like to stick around to ask questions, you're welcome to do so. So thank you.